Now, with the corpus-based approach to choosing the linguistic structures and configurations that we're going to test a model on, we get a lot of advantages. First of all, understanding relative frequencies of structures in naturalistic usage is important for understanding our linguistic environment. And it's important because artificial systems with applications will encounter more frequent structures more often, and it's important that they behave well in them. But if we want to gain real deep insight into the behavior and function of a system, whether it's an artificial system or humans, then having control over the stimuli is essential. That allows us to do targeted evaluation. We can choose stimuli that are likely to be more revealing to us about the performance and behavior of a system than the kinds of things that are necessarily common in the environment. And an example of this for subject-verb agreement is work by Marvin and Lenza in 2018, where they did controlled stimuli that had many different kinds of syntactic configurations, and they automatically generated a large number of stimuli, some of which were very sensible and some of which were a little more semantically weird, like the nonce colorless green sentences that we just saw. And there's a number of different kinds of configurations that you see here, including, for example, across a prepositional phrase. We saw examples of this a lot. Across a subject-relative clause, we didn't talk about that, but those are two different ways that you can put an attractor in between a subject and a verb. But the other content in between the subject and the verb besides the attractor is going to differ. And they also looked at across coordination structures, across inside object relative clauses. And the results were interesting and revealing. Now, first of all, for most structures, the LSTM that they looked at, this is the same Goulart-Dava LSTM for English that we talked about a moment ago, did actually near human level performance in a number of simple cases, and clearly better than the n-gram baseline, which is basically forced to 50% because of the distances between the subjects and the verbs in most cases. The RNN did well above the n-gram baseline in almost all cases. But actually, the situations that the RNN found the hardest and the situations that human found the hardest were not actually the same. And that's sort of interesting because earlier we saw a case where there was an asymmetry between a plural attractor for a singular subject eliciting more errors for both humans and for LSTMs than a singular attractor for a plural subject. But in this case, we see a difference in the pattern. The problems that are hardest for the RNN are the ones that actually there's a lot of material that intervenes in between the subject noun and the verb. The cases that are hardest for the human are the ones that we looked at in the comprehension setting. The case where the noun is actually immediately before, the subject is actually immediately before the verb, but there is a syntactically higher in the overall tree structure noun that has a different number. These are the inside object relative clause cases. Those are the hardest for the human. So there's actually a discrepancy between what's easiest for the model, what's hardest for the model versus what's easiest for the human, what's hardest for the human. So although LSTM models actually do have a number of interesting properties fall out of them for agreement patterns, they don't fully recapitulate a human-like processing pattern. And one last thing for today, which is not only to do behavioral testing, but to do a little bit of peering inside the machinery of a recurrent neural network language model to try to gain insight into how it achieves subject-verb agreement. So remember, this is the structure of an LSTM model, but remember that inside this little piece right here, what's being passed from one unit to the next in time is actually a big vector. This vector is a cell state. The bottom arrow is the hidden state. And the authors Lecretz et al. In a paper last year, just a year ago, actually found that you could get some pretty interesting insight into the behavior of this model by doing what's called ablation, which is once you've trained a model, you just knock out some of the units at various points in time. You force their values to be 0, and you see its effect on the behavior of the model. This is an intervention into the internal state of the model. What they found is that there were two particular nodes in the cell state. This is for the Goulart-Dava model, cell number 76 and number 988. And if you knocked out one or the other, then you actually could differentially affect the model's performance in subject-verb agreement. And actually, depending on which node you knocked out, you either made plural agreement worse or you made singular agreement worse. So if you knocked out, this is with their behavior, and the unablated model is here. It performs very well on a wide variety of configurations that they tested. If you knock out node 988, where then what you find is that for a number of cases where the verb should be singular, there is a decrease in performance. It was not the case that knocking out node 988 made performance worse for cases where the verb should be plural. These minuses represent cases where there was not an appreciable decrease in performance. In contrast, when you knocked out node 776, you had the opposite pattern. The cases where the verbs that should be plural were often impacted quite a bit, and the cases where the verb should be singular were not. Now, they did another really interesting thing, which is that then they looked at the behavior in the cell state for cases for each of these nodes in the cell state of what happened to the cell state activation at various points in processing a sentence. So this is a case where there's agreement across a prepositional phrase. The boy near the cars greets, the boys near the car greet, etc. And what they found is that when the subject noun phrase comes in, what they found is that for node 988, there was a deflection of the cell state. There seemed to be a recording in the activation level of this cell state of that was different for the singular noun than for a plural noun. So when the subject was singular, that's a blue line, you have a downward deflection. And you saw the opposite pattern in node 776. That there was a deflection downward. There seemed to be a recording of the number marking for the noun. Notice that the next noun that's encountered, car, does not actually appreciably affect the value for that cell state. So the system has not only learned to record, at least for this configuration, the subject number marking, but actually has learned to ignore the number marking on other nouns. Finally, you can see what happens when you actually encounter the verb. After you get to the verb, by the time you're at the next word, the difference seems to have been more or less erased. So information seems to be recorded about subject number at this point, and then once you get to a verb, that information seems to be more or less discharged. And that actually seems like a hierarchy-like behavior. So that's actually one of the most interesting and intriguing results that we have to date on understanding how syntactic-like behavior is achieved by a recurrent neural network model.